So how do we direct current through various parts of circuits? How do we adapt voltages to suit specific situations? How do we protect sensitive electronic components from excessive current? And how do we determine the overall current in a designed circuit before we make a mistake and burn out valuable electronics? Hello, I'm Mr. McBrien, and this is the Robotics Electrics Certification video number 3, Resistors. So, resistors, the way we look at them, aren't typically added to circuits in robotics. So we won't typically be including what we normally look at as resistors in our robot designs. And the reason why is because motors already have a pretty high resistance. So mainly we're going to be looking at resistors from the point of view of understanding how current is going to behave in our design circuits. So we're going to introduce the circuit components, resistors, and we'll talk about them briefly, but really we're going to focus on how resistors behave in circuits at the end of the discussion. Okay, so these are some cartoons of resistors. We'll use the metal film ones on the right typically. Now, you may have seen resistors before and noticed that there are colors. There are lines of color on the body of the resistor. And these actually have meaning. They're not decoration. 3 or 4 band colors are used for 5%, 10%, and 20% tolerance resistors. In other words, they have an uncertainty that's rather high. So the first 3 bands denote the rated value, and the 4th tells us the precision, how much it may vary from that rated value. And so the first band's the first digit, the second band's the second digit, and the third band is a multiplier, essentially a number of zeros. The 4th band then tells us how accurate that is. Okay, so here's a blow up of an individual resistor that's showing us how to read it. We have our first value that is a digit, our second value that's a digit, a multiplying factor. Red indicates 100. Then we'll see a gap and then a color that tells us the tolerance. So this resistor, green tells us it's a 5, blue is a 6, multiplied by 100 for red gives us 5,600 ohms. And we know it might be 5% less than that number, 5% more than that number due to our gold band. Okay, there are also much more accurate resistors, ones that are built to a better tolerance. And these can have very accurate values. In fact, some of them may be an error of only 1 part in 1,000 or 0.1%. So often these will have 5 color bands, with the first 3 bands indicating the value, the 4th band the multiplier, and the 5th band the tolerance. And so they would look something like this. Green indicating a 4, brown, black, red, and then our plus or minus 1%. Sorry, green indicating a 5, brown for a 1, black for a 0, red again is a 100 multiplier, and our accuracy of plus or minus 1%. And so what we see then is that this is a 51 kiloohm on the bottom resistor. Okay, are there other ways to determine what the resistances are of these components? Well, yes. We don't have to memorize those things or pull out a card and a calculator. We can put the colors into a website and determine the resistor value. Or we can use what we learned yesterday and use our multimeter and measure the resistance. Okay, so there are also resistors that aren't designed to be just one resistance. So there are things called variable resistors, These, we can change their resistance values, and there are a couple of different designs of these things. A potentiometer is a 3-terminal variable resistor that divides voltage. A rheostat is a variable resistor that controls current. And the symbols are given here. Resistors cannot handle an unlimited amount of current. We've alluded to this before, the fact that some components will be burned out by too high a current. In fact, there's a power rating for resistors related to how much heat they can dissipate before they get damaged by heat buildup. So the power rating is determined by the overall characteristics of the resistor, has nothing to do with the number of ohms, only has to do with the amount of heat it can dissipate. And these things are, the heat that they can dissipate is measured in watts, and really you don't want to get close to that rating. So if you're using a resistor that is right at its edge, right at its limit on a hot day, or on a day when you have a bit higher current running through your components, you're liable to burn it out. So you want to stay well below that rating. And really, all things being equal, you can tell power resistors because they're in fact bigger. Okay, if you do overheat a resistor, you'll know because it's going to get very hot. You may be able to see or smell the evidence of this. If you do have this problem, don't try to use that resistor again. It's better to remove it from your circuit and at the very least test it, but probably replace it. And while you're at it, why don't you replace it with a higher wattage resistor? Okay, with regards to combining resistors, this is where we're going to spend the majority of our attention for today. We can combine components in a circuit, and we need to understand what effect this has. And really there's two main ways you can combine different components in a circuit. We can combine them in series, one after the other, or we can put them beside each other in parallel. And resistors give a very different result depending on which way they're put into our circuit. So resistors in series, any components we put in series, they'll work together to slow down electron flow. And it's really a very simple relationship. Not often we get to do addition in our work. Well, in this case we get to. So the resistances simply add together. So in this case, our overall resistance of the circuit will be R1 plus R2 plus R3 plus R4. Now in contrast, resistors in parallel give an extra path for electrons to follow. So the current distributes between them, and when you put two resistors in parallel, the overall resistance goes down. And the relationship looks like this. If you have some time, you can go through and get a better understanding of this by using Ohm's law. But for now, we can just state that if we have a number of resistors in parallel, the relationship will be this. 1 over the overall resistance will be equal to 1 over R1 plus 1 over R2 plus 1 over R3, and so on. And our circuit, of course, looks like this. So as an example problem, resistors in parallel being really the more interesting problem, we can ask ourselves, what's the overall resistance of this circuit? By the way, from that, we can figure out the overall current and see if we're going to exceed some aspect of the circuit. So the overall resistance of this circuit, then, we can take our given, the resistances of the 3 individual resistors. Unknown, of course, is the overall resistance, and our equation is just the one we saw on the last page. When we substitute in, we get 1 over RT equals 1 over 10 kiloohms plus 1 over 2 kiloohms plus 1 over 1 kiloohms. And our solution, the overall resistance is 0.625 kiloohms, or 625 ohms if you prefer. Now, a suggestion. Some of us are really very good at dealing with fractions. Others are not. So a suggestion would be, considering the risk that's associated with getting these calculations wrong, it's probably a good idea to be very careful about the arithmetic in these cases. If you're not great with fractions, go ahead and use your calculator and use it carefully. And also, don't forget to ask yourself if your answer makes sense. Anytime you put resistors in parallel, the overall resistance should be less than for either of the individual resistors. So what about more complicated problems? And these things, by the way, are closer to the kind of things we might see inside our robots. We might see a whole group of different components that we want to consider in terms of an overall circuit. These, you could use one large math expression for these in order to get the overall resistance. In general, it's probably not worth the trouble. It's easier to just use a stepwise approach. So what we want to do is identify sets of parallel resistors and use the mathematics to essentially figure out what they would be if they were a single resistor. So figure out the resistance of a set of parallel resistors as one individual resistor, and then reconsider our circuit from there. And you can continue doing this this process until all you have left is a series problem. So let's go through a simple one now. So we could ask ourselves, what's the overall resistance of this circuit, where E is our power supply? Well, we need to recognize that we have resistors both in series and in parallel. And so what we want to do first is treat the parallel circuit, the parallel resistors, so that we can turn it into a series circuit. So we're going to treat these first. And we're going to essentially turn these into an individual resistor. So 1 over the overall resistance is equal to 1 over R1 plus 1 over R2. Substitute in 1 over R equals 1 over 50 plus 1 over 50. Or the overall resistance of this parallel part of the circuit is 25 ohms. Now with this in place, we can sort of redraw our circuit, and now we have a pure series circuit with 100 ohms, 25 ohms, and 50 ohms. And probably you can do that by examination and realize that the overall resistance of this then would be 175 ohms. So if you'd like to do some more thinking about these things, go ahead and do some research on voltage drop across a resistor. This is a very useful concept and an important one for us in our robotics. Okay, and in addition, work your way through the resistors worksheet and complete the certification test number 3 on Google Classroom, please. Thanks very much. Have a wonderful day.